Welcome to today's Explainer. So we're unpacking a really fascinating piece of research today that tackles two of the most stubborn environmental challenges of our time. We're going to look at how two massive everyday waste streams can actually be combined to create clean energy. And the whole thing is optimized by artificial intelligence. Okay, let's just dive right into it.
Think about this for a second. What do your morning coffee and the plastic packaging from your latest delivery have in common? Well, on the surface, absolutely nothing, right? One is completely organic and the other is totally synthetic. But globally, they share a pretty dark commonality. They're both piling up in our landfills at just an astonishing rate. But what if I told you that combining them might actually be the key to solving the waste problem for both?
Section 1. A brewing plastic problem.
To really understand the solution here, we first need to wrap our heads around the sheer scale of the challenge. The research we're looking at actually comes from Saudi Arabia, which is a region famous for its really high-quality Kaolani coffee. Now, as consumption over there rises, massive amounts of spent coffee grounds are just ending up in landfills. And at the exact same time, we've got this staggering buildup of polystyrene. You know, that's the synthetic plastic used in packaging that basically just refuses to degrade. So chemical engineers realized that to meet the UN Sustainable Development Goals and Saudi Vision 2030, they couldn't just keep burying this problem in the ground. They absolutely needed a circular economy solution to turn this trash into treasure.
Section 2. The magic of copyrolysis.
This brings us to the actual scientific process that acts as the catalyst for our magic recipe here. The core of this research revolves around a technique called copyrolysis. Basically, it's the thermal degradation of mixed materials, so in our case, coffee waste and plastic, heated at incredibly high temperatures in an environment totally devoid of oxygen. And because there's no oxygen present, the materials don't just burn up into ash and smoke. Instead, they break down chemically into some highly valuable byproducts like bio-oil and biochar.
But, here's where the problem gets a little tricky. These materials really do not like to break down at the same time. Pure coffee degrades somewhere between 226 and 386 degrees Celsius. Pure polystyrene, though, much more stubborn. It needs between 290 and 484 degrees. So if you try to process them separately, it's highly energy intensive and just super inefficient. But what happens when you mix them together in the exact same high heat reactor?
While the researchers found that blending these materials induces what they call a positive synergy, the volatile components in the coffee waste, like its amorphous hemicellulose, actually begin to crack and break down at lower temperatures. And as they do, they go on the offensive. They attack and weaken the really stubborn chemical bonds of the polystyrene matrix. So the coffee literally helps tear the plastic apart.
The absolutely crucial point to take away here is the sheer scale of this chemical transformation. The coffee acts as an initial destabilizer, and as that intense heat is applied, the solid plastic matrix breaks down, its volatile carbon-heavy components are basically swept away, and it transforms into this highly porous sponge-like structure. The data here is just incredible. The carbon content of the solid material drops from over 76% all the way down to just 6.1%. And what you're left with is an oxygen-rich, super valuable biochar.
Section 3. Finding the perfect blend.
Chemistry is basically just cooking, right? And like any good recipe, success relies entirely on finding the exact mathematical proportions. To figure out the perfect blend, scientists measure something called activation energy. You can think of this as the energy barrier, or a hurdle, that has to be overcome just to get this thermal breakdown process started. Obviously, the lower the hurdle, the less energy we have to spend to run the industrial bioreactors, and that makes the whole process cheaper and way more sustainable.
And the data builds a really compelling case. Pure plastic has an energy hurdle of around 90 kilojoules per mole. But when the researchers created a 50% blend, so exactly half coffee and half plastic, that activation energy actually dropped to between 87 and 92. The coffee and plastic are just working together perfectly here, creating a highly reactive, efficient breakdown.
So 50% is our golden ratio. A 50-50 split allows an industrial bioreactor to operate with the absolute highest energy efficiency. That means we need significantly less heat to initiate and sustain the breakdown of all this waste.
But okay, here's the plot twist. You might be thinking, hey, if the coffee helps break down the plastic, let's just dump in way more coffee, right? Actually, no. When they tested a 75% coffee blend, the activation energy skyrocketed to nearly 187 kilojoules per mole. Why? Well, because adding too much coffee creates excess biochar really early in the process. And this char acts as a physical barrier. It shifts the reaction so that it's suddenly way harder for the heat to reach and break down the remaining plastic. So more is definitely not always better.
Section 4. AI predicts the process. Now, as you can imagine, running thousands of physical experiments in a lab just to find these exact thermal dynamics is incredibly expensive and honestly super time-consuming. And that is exactly where modern technology steps in. The researchers turned to machine learning to model this complex chemical breakdown. They compared a deep neural network, or DNN, against a k-nearest neighbors, or KNN model. And while the deep neural network performed exceptionally well, the KNN model was astonishing. Using 100 neighbors and Chebyshev distance calculation, it achieved near-perfect predictive accuracy, with an R-squared value of practically 1.0. It basically acted like a master pattern-matching detective, perfectly predicting the localized nonlinear stages of the thermal breakdown.
So here's how the AI actually pulls this off. Step 1. The researchers input the operating parameters, things like temperature, heating rate, time, and the blend ratio. Step 2, the AI maps out the highly nonlinear thermal breakdown stages, literally learning how the coffee and plastic interact at every microsecond. And Step 3, it accurately predicts the exact mass loss. This is a huge deal because it means engineers can now design massive industrial bioreactors virtually without going through endless, expensive trial and error.
And the AI revealed some pretty fascinating insights about the process through a Pearson correlation matrix. It proved that temperature is the undisputed master chef here. It's the absolute primary driver of mass loss. Time is a moderate factor, but surprisingly, slight variations in the exact mixture composition, once you're near that optimal zone, they don't drastically alter the overall curve shape. This is brilliant news for the real world, because let's face it, municipal waste streams are never perfectly uniform. This tells us the process is robust enough to handle the messy realities of everyday trash.
Section 5. Fueling a circular economy.
And that brings us to the ultimate goal of all this laboratory science and AI modeling. As the researchers concluded, this isn't just some neat science experiment. This actually provides a scalable framework for municipal solid waste management. By figuring out the thermokinetics and using AI to map the exact pathways, we can effectively transform our common, everyday waste streams, materials that would otherwise just sit in a landfill for centuries, into highly valuable bioenergy assets.
It completely changes our perspective on what we throw away. When you combine a bit of human ingenuity, some extreme heat, and artificial intelligence, the things we thought were completely useless literally become the fuel of the future. So, knowing this magic recipe, will you ever look at your morning trash the same way again? Thank you so much for joining me for this explainer. Stay curious and keep learning.